Hello class, today we are going to name organic compounds using the IUPAC naming system rules, and we're going to go over examples. So in this first two problems, we're going to identify and name the parent chain in each of the following compounds. As a review, the parent chain is the longest consecutive chain of carbons. So the way we can approach this problem is first to look at the straight chain that naturally occurs as we go across. And we can count that and check to see how many carbons it is. Here I see 1, 2, 3, 4, 5 carbons. Now I have to ask myself, is that the longest possibility? What if at this point we decided to go upwards with our chain and we go 1, 2, 3, 4, 5, 6. By going upwards, we find that the longest chain is actually 6 carbons. So if we are choosing between the two, the longest parent chain is this one. And on this parent chain, we only have one branch. Now, since it is a 6-carbon chain, I need the prefix that represents 6, which is hex. And then I know for an alkane, the ending is ane. So this is hexane, which is C6H14 as the main formula for the parent. And then I know I'm going to have an extra carbon on there with 3 hydrogens. So I don't actually care about the formula for right now, but I do care about the parent name. If I go through and try this on the next one, I see this chain going through the center. That is 1, 2, 3, 4, 5, 6, 7 carbons long. Let's see if there are any other options. If I went down, I would go 5, 6, 7 as well. So this would be 5. I should change the color on that, I'm sorry. I could also go 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 that way. Are there any other options? Let's see. I could also go. Would that give me a longer option? 1, 2, 3, 4, 5, 6, 7. All right. Or going in the reverse direction would also give me 7. So I have 3 possibilities here for a 7-carbon parent chain. So first, I know that 7 carbons has a prefix of hept, and I add my ane ending. So either way we spin it, this is going to be a 7-carbon chain. What we need to figure out is which of these 3 possible 7-carbon chains is the best. Remember the rule for our 7-carbon chain. Apologies, I'll just erase some things instead of clearing the whole board. The rules for figuring out our best parent chain is to have the most substituents or the most branches on the parent chain. If I go through this chain down the center, I've got 1, 2, 3 branches. If I choose to go this way, I only have 2 branches. So I know I'm not going to use this chain. I can eliminate that one. The other option I had is going this way, which also gives me 2 branches, so I can eliminate that one. The best parent chain in this particular problem is the one that goes right through the middle and has 3 branches. And again, we said this is going to be a heptane. So that's the process you're going to use for identifying a parent chain. Sometimes it requires a little bit of trial and error in order to figure out. It is okay to go back and erase your parent chain once you've figured it out and figure out which one really is the parent chain. So let's go through and figure out our numbering system. So if we go back to our hexane example, I know I could number in this direction from top down to bottom, or I could number in the reverse direction Now, there's only one branch on this particular hexane chain, and my options are looking at having that branch on 3 or on 4. Remember, I want to go with the lowest number. So numbering in red that goes down this way is the best numbering system from top to bottom. Now I have to name my branch. This is a 1-carbon branch, which means it is a methyl group. And that methyl group pops up on the 3rd carbon. If I put that together with my name, I get 3-methyl hexane as the systematic name for this compound. If I move on to the next one, I know I can name number from left to right. I also know I can number from right to left. Now this one's interesting because it's actually a symmetrical molecule at this point. The group here is a 3-carbon group. We're going to name that propyl for 3 carbons. And these other groups are 1-carbon groups. So these are both going to be methyl groups. Now, you'll notice that I have a methyl on 3 and a methyl on 5 in one direction, and I also have a methyl on 3 and a methyl on 5 in the other direction. So in this particular example, it doesn't matter which way you number because you end up with the same result. It is symmetrical. I'm going to say let's number from left to right, just for sanity's sake. And then I need to put numbers for each of my substituents. So I know I have a 3-methyl. I know I have a 5-methyl. And then we said 4 for the propyl group. Now remember, if you have the same substituent popping up twice, it's a lot to write out 3-methyl, 5-methyl. So we can use a prefix, this case di means 2, to combine parts of our substituents when we name them. So let's do that. I know that M comes before P, so methyl will be before propyl. So I'm going to have 3,5-dimethyl. I'll combine those two. Now keep in mind the di prefix is not part of the alphabetization. Then I have 4-propyl, and then the last part of my name, which is my parent chain, heptane. Now I'll be honest, I put a dash in between propyl and hexane, or heptane, and I didn't need to do that, so I apologize. So I would just stop here. So the answer for this one is 3,5-dimethyl 4-propyl heptane. As you go through, you'll see it's pretty systematic. You start with the parent chain, then you work on your numbering, then you name your branches, and then you put the numbers with the branches, and you alphabetize your branches, and you put it all together. It's the same system every time. So let's do another example. This one, we're given a condensed structure. My longest parent chain seems to actually be this one going all the way across. So I'm going to go through and count my carbons. All right. Now the other way I could have numbered was from right to left, but I quickly will see that my first branch when I number from right to left ends up on 4, whereas here my first branch ends up on 3. So I am going to number from left to right because that gives me the lowest possible branches here. So I'll erase that right to left numbering. I know my parent chain, 8 carbons, is going to be octane. And then I need to identify my branches. This is a 1-carbon branch, so this will be 3-methyl. This is a 2-carbon branch, so this will be 5. ethyl. Then I need to alphabetize based off of the branch name. E comes before M, so this is going to be 5-ethyl 3-methyl octane. Notice that it doesn't matter where the numbers are. The numbers do not have to be sequential, but the alphabetization of these branches is what matters. So 5 can come before 3 as long as it's paired up with a branch that comes first alphabetically. Here's another example dealing with bond line structure. We're going to have to find the longest possible chain here. So the longest possible chain, I think, still is this one that goes through the center. And when I go that direction, I end up with 4 substituents. I have a substituent here, 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 and here. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon parent chain. 10 carbons tells me this is decane. Oops, spell. This is decane. Now I got to figure out my numbering. If I number from right to left, 1, 2, 3, 4 is my first substituent. If I number from left to right, 1, 2, 3 is my first substituent. So I'm going to number from left to right on this one. I got 4, 5, 6, 7, 8, 9, 10. Now I have 2 types of groups here. I've got a methyl group here. I've got an ethyl group because there's 2 carbons, and then these are also both ethyl groups. So remember, when you have multiple of the same group, you need to combine them using a prefix. So ethyl, since there's 3 ethyl groups, we're going to make it triethyl. And we're going to list the numbers. So we have 3, 3, because there's 2 of them on the same carbon, 6, triethyl, and then 7 for our methyl group, 7-methyl decane. And that would be our final name. Here's another one. If we read carefully here, you'll see that on this carbon, you actually have 2 chlorines sticking off here. So this is a good time to talk about chlorine. The halogens, as substituents, become something that looks like this. So chlorine becomes chloro, bromine becomes bromo, iodine becomes iodo, and fluorine becomes fluoro. So they just chopped off the -ine ending and turn it to an O ending. So I have some substituents to look out for here. I got to find my longest chain. So I've got 1, 2, 3, 4. This is my 5th carbon. And then if I go down here, this is 6, 7, 8 is my longest chain. If I continued here, it only would have left me off with 7. So this is going to be an octane as my parent chain. And then I have an ethyl group on 5, and I have 2 chloro groups on the 2nd carbon. So 2,2-dichloro 5-ethyl octane. I'll bring the octane closer, so that's part of the name. Keep an eye out for those in condensed structure. What's really happening is these chloro groups are sticking off of here. They're just written after the carbon because that's the carbon they're attached to. And then this carbon here is attached to the next carbon, just like it's attached to the previous carbon. All right, the last thing for today is to draw these things in bond line notation when you are given a name. So I always start with the parent first. So the parent is hexane. So I'm going to draw a 6-carbon chain. 1, 2, 3, 4, 5, 6. And then it says dimethyl. So methyl is 1 carbon, and I've got one sticking off the 2nd position, and I also have one sticking off of the 3rd position. So if I were to clean that up, this would be the bond line notation for 2,3-dimethyl hexane. Now, if you were to do a condensed notation, you could also do your carbon chain. I've got 3 carbons in a row, and sticking off of my first carbon is CH3. Notice I wrote 1 less H because this carbon is bonded here, here, and here. So since it's got 1 branch, there's 1 less H. And then I did the same thing over here for the 3rd carbon. This would be the condensed structure for this molecule. I'm not going to do condensed for all of these because it didn't ask for it, but you might see that on another worksheet. So that is something you could draw as well. We can go through and do 3,4-diethylhexane. Again, we're going to draw our hexane chain first. And then on 3, I've got 2 carbons sticking off. On 4, I also have 2 carbons sticking off. Now, I did kind of fudge that a little bit. So you can clean up your structure, and then you'd have something that looks like this. Now, when I drew my ethyl groups, I did down and then this way, but you could have also gone down and this way. It's just a preference. As long as the zigzags are clear and you can tell that the vertices where the lines meet are a carbon, that's what's important. All right, the next one we've got nonane, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And on the 3rd is a methyl, on the 5th is a methyl, and then on the 6th is a methyl. And then my last one, as another example, we've got octane. 1, 2, 3, 4, 5, 6, 7, 8. 2, 2-dimethyl, so there's a methyl sticking off of each. And on the 4th carbon is a propyl group. So propyl is 1, 2, 3 carbons, so 1, 2, 3. And I chose it sticking off to the right just so it didn't get in the way of the other methyl groups, but you could have drawn it sticking off to the left. All right, time to go forth and practice a bit more. I'll see you in the next lesson.